In this video, we're going to be discussing the concept of solution stoichiometry. This is a combination of the stoichiometry we did in our previous chapter, as well as the new concept of concentration, specifically molarity, that we brought up in this chapter. Here's a quick rundown of some of the objectives. We're going to start with a very quick reminder of what stoichiometry is all about, some of the details. We'll talk about concentration, which we've already learned about in the form of molarity. We're now going to talk about it in terms of how it can be used as a conversion factor. And then last but not least, we'll talk about how that conversion factor can be applied in stoichiometry calculations. The picture to the right shows a very common apparatus used in chemistry that we'll use later in this chapter. This is a process known as a titration. Titrations are very common calculations for determining the concentration of unknown substances like an acid, and we'll be using solution stoichiometry to do the math after we get the data from an apparatus such as this one. So this will be a calculation we use throughout the chapter. Just a quick reminder of what stoichiometry is all about. The real definition is this guy right here. It's a calculation used to predict the outcome of a chemical reaction based on the balanced chemical reaction itself, which provides us data that supports conservation of matter and the amount of starting material used. Here is yet another example of a stoichiometry calculation. We have a balanced chemical reaction at the top, and the question asks us how many grams of water will be formed by completely reacting 20.00 grams of the hydrogen gas. Probably not a terrible idea to take a moment, pause the video, give this problem a try. I'll go through the answer in about 10 seconds. So here's the worked out math for the answer to this stoichiometry calculation. We started with the 20 grams over here that we were told about we had in the problem. We used the molar mass of hydrogen gas to convert it into moles. This right here is our mole to mole ratio, the key stoichiometry step, and the numbers come again from the balanced chemical reaction. This converts us for how many moles of hydrogen we start with to how many moles of water we're going to get. And then last but not least, we convert the answer from moles of water into grams to get our final answer of 178.7 grams of water from our 20 grams of hydrogen gas. If you're not comfortable doing these types of calculations, adding something else to it today is certainly not going to help that situation. Go back and review the videos on stoichiometry, try a couple more problems, and then come back to this one. Now, let's start folding in some of the new information. We've already talked about the fact that molarity is the moles of solute per liter of solution. And if you recall, the solute is what is being dissolved, and the solution is what we're dissolving into. And we can represent this with an equation as well. M, molarity, is equal to moles of solute divided by liters of solution. Hopefully you're already starting to realize and see the formatting of this. It looks a lot like the conversion factors we've been using in our dimensional analysis throughout the year, and this is exactly how we're going to use it in a minute. What this will convert between us when it is a conversion factor is it'll convert between the volume of our solution and the amount of solute, which eventually be our reactant, in the actual solution itself. So it's a conversion factor that links these two ideas together. Moles of solute, liters of solution. So without even getting into how to use concentration as a conversion factor, we can actually tackle a problem such as this one. This question asks us how many, and I left a word out here, how many moles of solute are in 0.75 liter solution of a 2.0 molar solution of sodium chloride in water. We can actually use the equation for molarity to figure this out, plug in the volume of 0.75 liters and the concentration of 2.0 molarity, and then solve for the value of x to find out that there are 1.5 moles of sodium chloride in this volume of this concentration of solution. However, the point of this particular section is not to do this algebraically, but instead to use dimensional analysis. Recognize that 2.0 molars is really 2.0 moles of solute for every 1 liter of solution, and we can write this problem as a dimensional analysis problem. Here is our molarity right here, being used as a conversion factor. And now we've lined it up so that the volume of the solution gets canceled in the dimensional analysis. This leaves us with the moles of solute left over, and notice we get the same answer we got when we solved this problem algebraically. I don't think either one of these methods is necessarily easier than one another, but when we're trying to do stoichiometry, we need to be able to do the math in this particular format as opposed to doing it algebraically up above. Now, before we dive into the actual stoichiometry problem itself, you can take a look here, and this is a document we kind of talked about earlier in the chapter, actually in the last chapter. We were using this part of the conversion. This is our mole conversions that we have available to us, and I told you to ignore the top part until we get a little further on in the year. Well, here we are. Now we can add this in here, and it shows us again, this is our molarity, and this is our molarity here, written one way versus the other, and now we can convert between the solution volume and the number of moles that we have in a sample, just so we can convert mass to moles, number of particle moles, or the volume of a gas in moles at standard temperature and pressure. So again, just introducing yet another conversion factor that we can use in our arsenal of stoichiometry problems. If you don't have a copy of this document and you want to use it later on, it is linked at the bottom of the page down below. Pause the video, download and print out the document, and you'll have it available to you while you work on problems. So this brings us then to the main events, solution stoichiometry itself. What solution stoichiometry is are basically stoichiometry calculations that start or end with a volume of solution instead of things like mass, number of particles or moles, or a volume of gas. These are the problems we've done earlier in last chapter. This is the material over here that is new. When we're doing solution stoichiometry problems, it's typically the solute is what we're interested in. That's the actual reactant that's going to be reacting with our other chemicals to produce a certain quantity of product. However, what we can measure is actually the volume of the solution. So what we need is a conversion factor that links the two of these guys together, and that's going to be our molarity. It's the volume of solution, or it's a moles of solute per volume of solution. And that's exactly what we're talking about down here. The molarity then can be used as a conversion factor to link these two constants together. What we can measure versus what we need to know for the stoichiometry problem. So without further ado, let's take a look at an actual problem. The question here is how many grams of our silver chloride can be formed by completely reacting 5.0 liters of a 0.75 molar solution of silver nitrate. So notice again here in bold, instead of giving us mass or a certain number of moles or something like this, now we have a volume and a concentration of solution. Just like any stoichiometry problem, the first order of business is to ensure that our chemical reaction is balanced. We'll take some time to identify the key chemicals we're dealing with in here. In this case, it's going to be the silver nitrate and the silver chloride. And then we're going to start setting up our actual stoichiometry problem. If you feel like you know what you're doing at this point, go ahead and give it a try on your own. If you're not sure what's going on, I'm going to work through this problem in just a couple seconds. So we'll start the problem then by writing out the given value we have. We have 5.00 liters of silver nitrate. And just like in any stoichiometry problem, we have to eventually get into moles so that we can use this data in the form of a mole-to-mole ratio. Well, here's where our molarity comes into play. We can recognize that 0.75 m is really 0.75 moles of our AgNO3 for every 1 liter of solution. And we can introduce this as a conversion factor right here to convert us from liters into moles of our silver nitrate. Once we've gotten to moles of silver nitrate, we can introduce our mole-to-mole ratio. In this case, it is 2 to 2 based on the balanced chemical reaction. And then the question wanted to have an answer in grams, so our last step would be to convert moles of silver chloride into grams of silver chloride using its molar mass. Punch all this stuff into your calculator just like we always do. Make sure everything cancels out right, and then you'll get an answer of 537 grams of silver chloride using the correct number of significant digits as determined by the initial starting volume. Although I guess probably should have rounded to 2 sig digs, huh? So that's pretty much it. Hopefully what you're seeing at this stage in the game that this is not all that much different. We just have a new conversion factor to do the same exact math we've been doing all along. So what you should be able to do at this stage in the game is to use molarity as a conversion factor between the volume of a solution and the amount of solute that it contains. And then finally, to use molarity of a conversion factor in stoichiometry problems as well. So you should be able to use it in and out of those. As always in class, we'll take more time to answer questions that go along with this and certainly do a couple problems together until you guys start to feel a little more comfortable.